Welcome back to OwlsPrep. Topic 1.5, Polynomial Functions and Complex Zeros. This topic is big enough that we've split it in two. Part 1. This video is entirely about one question. What happens where a polynomial equals 0? Those inputs control almost everything. How the polynomial factors, where its graph meets the axis, and what the graph does when it gets there. Part 2 will pick up the two things in this topic that aren't about zeros at all. If p of a equals 0, then a is a root of the equation p of x equals 0, and the same number is called a zero of the function p. Root belongs to the equation, 0 belongs to the function. They are two names for one value. And for a real number, there's a two-way street. X minus a is a factor of p exactly when it is a zero of p. Spot the factor, you know the zero. Find the zero, you know the factor. Now look at our example. P of x equals x plus 2 times x minus 1 squared times x squared plus 4. The factor x minus 1 appears twice, so the 0, 1 has multiplicity 2. That is what multiplicity counts. And here's the payoff. A polynomial function of degree n has exactly n complex zeros, counting multiplicities. One word there needs care. In mathematics, complex includes real. A real number is just a complex number with no I attached. So n complex zeros means the total number of zeros is n, real ones and non-real ones together. It is not a count of the ones with an I in them. Check it here. Multiply out the factors, and the degree is 5, so there must be 5 zeros. -2, 1, and 1 again are real, that is 3. 2i and -2i are non-real, that is 2 more. 3 plus 2 is 5, exactly as promised. Here is the simplest way to see the real zeros. The graph meets the x-axis exactly where p of x is 0. Every place the curve reaches the axis is a real zero, and every real zero puts the curve on the axis. 2i and -2i never reach the axis, which is precisely why they are nowhere on this picture. Now, the curve can meet the axis in two different ways. At x equals -2, it passes straight through. It was below, now it is above, so the sign flipped. At x equals 1, it comes down, touches, and goes back up the way it came, staying positive on both sides. Both are real zeros. What differs is only how the curve meets the axis. That gives you two things. If the sign ever changes, the curve had to cross to do it. So a sign change always guarantees a real zero. And since the sign can only change where the curve meets the axis, the real zeros bound stretches on which the sign never changes. So to solve an inequality like p of x greater than or equal to 0, you just test one point in each stretch. Which of the two meetings you get is decided by multiplicity, that is next. So, crossing or touching, what decides it? Multiplicity. It does more than balance the zero count. It decides exactly what the graph does at each intercept. At x equals -2, our factor is x plus 2 to the first power, multiplicity 1, which is odd. Check the outputs either side. At -2.15 it's negative, at -1.85 it's positive. The sign changes, so the graph crosses. At x equals 1 the factor is x minus 1 squared, multiplicity 2, which is even. At 0.85 the output is positive, and at 1.15 it's positive 2. Same sign on both sides, so the curve comes down to the axis, touches it, and turns back without passing through. That's what even multiplicity means. The graph is tangent to the x-axis there. Now the zeros that don't show up. If a plus bi is a non-real zero of a polynomial with real coefficients, then its conjugate, a minus bi, is a zero as well. They always travel as a pair. In our example, the factor x squared plus 4 gives 2i and -2i, mirror images across the real axis. Now multiply that pair of factors back together, x minus 2i times x plus 2i. The I terms cancel each other out, and what is left is x squared plus 4, an ordinary quadratic with real coefficients, no I anywhere in it. That is how a perfectly normal-looking factor can be hiding a pair of non-real zeros. There is a counting consequence too, and it needs one piece of vocabulary first. Odd degree simply means the highest power is an odd number, 3, 5, 7, and so on. Our p has degree 5, so it has 5 zeros altogether. The non-real ones arrive in pairs, so they always use up an even number of those 5. Here that is one pair, 2 zeros. 5 minus 2 leaves 3, and those 3 are real. That argument works every time. Start from an odd total, take away an even number, and what remains is still odd, so it can never be 0. An odd-degree polynomial with real coefficients therefore always has at least one real 0, which is another way of saying its graph has to cross the x-axis somewhere. So that's part 1. For a real value, being a 0 and giving a linear factor are the same thing. A repeated factor gives multiplicity, and a degree n polynomial has exactly n complex zeros once you count them properly. The graph meets the x-axis exactly at the real zeros, passing through when the multiplicity is odd, resting tangent to it when the multiplicity is even. And any non-real zero arrives with its conjugate, which is why an odd degree always leaves at least one real 0 behind. In part 2, we'll find a polynomial's degree from nothing but a table of numbers, and work out when a polynomial is even or odd. See you there.